Alright, so this lecture will talk about different types of filters. But we'll begin with one more transfer function and its Bode plot before moving on to filters. So the transfer function is a third order transfer function, and the order of a transfer function refers actually to the order of the denominator polynomial in the transfer function. So here the denominator has an omega cubed, which is a third order, therefore this is called a third order function. And the order of a transfer function of an electronic circuit gets decided by the number of energy storage elements in that circuit. So third order function indicates that there must be three independent energy storage elements in that circuit. Alright, so we want to draw the Bode plot, the magnitude Bode plot of this transfer function. So first we write the magnitude, which is simply a0 by square root of the 1 plus omega squared by p1 squared, etc. And now we look at various frequency ranges over which this function can be simplified, as we did last time for first order functions. Alright, so this is a function. So we say, well, let us first look at, okay, I'm sorry, I didn't mention somewhere that let's assume that P1 is much less than P2 is much less than P3. So we start with the frequency much less than all three frequencies P1, P2, P3. And for that frequency, then all these three omega terms in the denominator can be neglected and leaving just a 1. So the gain is simply a0. For the frequency range where omega is between P1 and P2, so omega is much greater than P1. So this first term will be much greater than 1. And the second and third term will be much less than 1. So we'll get only the omega squared by P1 squared, the square root of that in the approximate expression. So we get a0 by omega by P1. And when we take 20 log, this is of course the same as a first order transfer function. So we'll get 20 log a equal to 20 log a0 P1 minus 20 log omega. There is an omega in the denominator. So the slope in this part of the Bode plot will be minus 20 dB per decade. For the frequency range where P1, P2 are both much less than omega, but omega is still much less than P3, then both these terms will be much greater than 1. This will be much less than 1. So approximately we'll get a0 by omega by P1 times omega by P2. So when we do the log, so we'll get 20 log a, 20 log a0 P1 P2 minus 20 log omega squared, and 20 log omega squared is 40 log omega. So the slope of this part of the characteristic will be minus 40 dB per decade. And similarly for omega much greater than P3, all the three terms in the denominator will contribute and we'll get a slope of minus 60 dB per decade. So the slope becomes steeper and steeper with increasing frequency for this transfer function. So the Bode plot looks like this: flat for low frequencies after P1 minus 20 dB per decade, after P2 minus 40, after P3 minus 60. This transfer function is actually very common in high gain amplifier characteristics, but we'll look at these next semester when we'll actually design such amplifiers. Alright, so now let us discuss filters. Suppose in this transfer function that we just discussed, if P1 and P2 and P3 were all equal, then this would become this, the one term cubed 3 times, so cubed. And if you were to draw a Bode plot of this, then, so in fact what I have plotted here are plots for 3 different orders. So suppose this 3 was n, then for n equal to 1, 2, 3, we'll get these 3 plots. So n equal to 1, we'll get minus 20 dB, which we have seen last time. If n were 2, it will be minus 40 dB. If n were 3, this will be minus 60 dB per decade. So this is called a third order filter. Of course, these are all low pass filters. So this is a third order low pass filter. This is a second order low pass filter and a first order low pass filter. Now, in real life applications, the need of the order of the filter is determined by how steep we want the gain of the filter to fall off above the corner frequency. And this depends on various applications. You will study more about these in your communication courses, where these filters are most widely used. In fact, there are applications where one needs filters of the order of 12 also and 14 also, but we are not going to go there. Okay, so here I'm putting here a bunch of second order filter circuits, second order. All right, so this will have two energy storage elements, and these are all the circuits I'm going to show you are all with two capacitive elements. All right, so here is a second order low pass circuit. So this RC is a first order circuit, but if we have another RC section, so two RC sections, this becomes a second order low pass circuit, and the circuit has a gain of 1 plus R1 prime by R1 at low frequencies. If you want to convert this to a high pass circuit, what one does is one interchanges these R's and C's. All right, so this circuit, the R's and C are interchanged, everything else remains the same. This becomes a second order high pass circuit. Now I'd like you to, as an exercise or homework, derive the transfer functions of each of these circuits. So find VO by Vs, assuming Vs is some sinusoidal signal of frequency omega. So derive the transfer function and then draw a Bode plot of this. All right, do this as homework. This one, the low pass as well as the high pass circuit. Now let's talk about a band pass filter. A band pass filter allows a band of frequencies to pass through. So it will not allow frequencies below a certain value and frequencies above another certain value. So it will allow only a band of frequencies. So here is a Bode plot. We'll arrive at a Bode plot in just a minute. So this is a Bode plot of a low pass filter. Now suppose we have a high pass filter that is kind of follows this low pass filter. Then the high pass filter will have this blue characteristic, and the combination of the low pass and the high pass will have this blue, then flat, and the black characteristic. All right, so this combined characteristic is a band pass filter that allows frequencies from omega 1 to omega 2 to pass through, and frequencies below omega 1 it attenuates, frequencies above omega 2 it attenuates. This is of course called a first order filter because these slopes are minus 20 dB per decade, well plus 20 or minus 20. If these were both 40, then that will become a second order band pass filter. Here is a circuit of a second order band pass filter. So it has two capacitors, but this is kind of the R2 C2 is a high pass section and C1 R3 is a low pass section, if you think about it. All right, in fact you should think about it, and also, as I said earlier, derive the transfer function for this and draw the Bode plot of that transfer function. Here is another band pass circuit which is more complex and it is very peculiar. This is called a Salon-Key filter, but it has very fascinating and interesting characteristics. Again, derive the transfer function, draw the Bode plot. All right. For band passes, so this band pass filter, so we kind of did one low pass and then one high pass. The high pass corner frequency must be lower than the low pass corner frequency. Only then it makes a band pass, right? So you can imagine if omega 1 was greater than omega 2, then this whole blue will move further away, and that is also a filter. It is called a notch filter, but it is a different type of filter. It is in fact another word for it is a band reject filter. But that's all. This is just for your information. All right. So let us think a minute about, suppose I want to design an 8th order filter. All right. Now the general kind of the one common method of designing an 8th order filter is to cascade second order filters. So I have shown it here. So let's say this K is 2, then this is a second order filter. So what one does is one connects the output of the second order filter to another second order filter, and the output of that filter to another second order filter, and this complete chain then forms a 2 times 3, so a 6th order filter. All right. And if I have only 2, that will be a 4th order filter with K equal to 2. So if I want an 8th order, I'll add one more second order section here, and so on and so forth. So one can think of making a 10th or a 12th or a 16th order filter just by cascading second order filters. Note that one can do the same thing for a band pass. So either this can be a band pass, second order band pass filter, or if I have a second order low pass followed by a second order high pass, then at the end of these two sections I'll get a second order band pass. All right, and so on and so forth. Okay, as I've made a comment here, filter design is actually an extremely complicated subject. It is usually a specialized postgraduate course. In fact, it is so specialized that we don't even offer it here at IIITB. But it is because it is complex and it requires a lot of theory and circuit design and all that. So what we've done here is just the very, very, very extremely basics of filter design. All right. Also note two things. Well, one thing I already said, that when we cascade, so the output of one circuit is connected to the input of the other, we must be careful about taking care of loading. So we've discussed loading before. So the connecting of this should not change the characteristic of this because of loading. So one has to be careful. All right. Okay. Now I want to discuss another circuit. The circuit we have seen before, the parallel RLC circuit. But earlier we saw this circuit for transient analysis. Now we look at this circuit for sinusoidal steady state frequency response analysis. And as I have said before, this is one of the most widely used circuits in communication receivers, and in the next few minutes we'll see why it is used. All right, so what we are saying is, let IS be a sinusoidal current source, and let's assume that the magnitude or the amplitude of IS is 1 ampere, 1 cos omega t. Then the voltage V will be IS times the Z of RL and C in the frequency domain. And I'm saying let IS have an amplitude of 1. So then the magnitude of V will be the same as the magnitude of Z because IS is 1. So I'm going to look at only at the magnitude at Z, but the everything we say about Z applies to V because IS is assumed to be 1. Alright, so Z is of course a parallel combination of R 1 by R j omega L and 1 by j omega C, which is this. So 1 by Z is 1 by R plus 1 by j omega L plus j omega C, and we take R j omega L common, and so we get j omega L plus R minus omega squared LCR when we cross multiply. And then so Z is the reciprocal of this, so this is j omega LR by all this. All right. So that is the same here. Now I'm rewriting this in a particular form. So I'm dividing by j omega, the numerator and denominator by j omega L. So the numerator becomes 1. this j omega L by j omega L becomes 1, and the rest of it becomes minus j into r by omega L minus omega CR. And we take the omega r out, so this is 1 by omega L minus omega C, which is omega squared LC minus 1 by omega L. Alright, now let us think about this expression. What this expression is telling us is that as omega is varied across a wide range, there will be one value of omega at which omega squared LC minus 1 will become 0. Alright, when that becomes 0, this whole imaginary term becomes 0, and Z, the total impedance of the parallel RLC circuit, becomes equal to just R, which is purely resistive. This frequency omega squared LC equal to 1, which means that omega is 1 by square root of LC, is usually represented as omega naught, omega 0, and it is called the resonance frequency of the circuit. The resonance frequency of a circuit is defined as a frequency at which the imaginary part of the impedance of that circuit becomes 0. Of course, this is not always the case for any arbitrary circuit. There are only a class of circuits which are called as resonance circuits for which the impedance becomes 0. The imaginary part of the impedance becomes 0. So at that frequency then, Z is equal to R and the voltage equal to Is times R can become arbitrarily large if R is large. Alright, now R, so let's go back to this. R in this circuit is actually, so in actual applications, there is never an R physically connected to the LNC. It is in fact, one wants R to be as large as possible. So ideally, if you don't connect it, it is just infinite. But there is an R that appears due to the non-ideality of the current source, which causes an R in parallel with Is, and also the non-ideality of the capacitor. So generally real life capacitors are never ideal, so there is always some leakage of current from one plate to the other, and that leakage is represented by a capacitor in parallel through which current can flow basically across the capacitor. But both these resistances, the R of the Is and the R of the capacitor, can be quite large, and therefore this R can be quite large, and so the voltage that can appear across these circuits can become very large, and this is the beauty and the utility of this circuit. So even for Is small, V can be large. Alright, let's look at the frequency response. So for that we'll write two more forms so that the same thing can be written in this peculiar form, R square root C by L into omega square LC minus 1 divided by omega square root LC, which can further be written as where omega naught is 1 by square root of LC, and this R square root C by L is called the Q, which is a quality factor of this resonance circuit. So we'll come to this in a minute. This can be written once more, which I have written here. So this is omega, this divided by this minus 1 by omega naught turns out to be omega by omega naught minus omega naught by omega. So this is the Z of our parallel RLC circuit. Now let us look at the frequency response. So we look at this Z for various ranges. So we say for omega much less than omega naught, this is very small, this is very large, and so the magnitude of Z will have only this term. This is much greater than 1, this is much less than 1. So we'll get R by Q omega naught by omega, R by Q omega naught, and the omega goes up. So the magnitude varies directly as omega. So on a dB versus log omega plot, this will give us a slope of plus 20 dB per decade. For omega much greater than omega naught, this is very large, this is very small, this is very large compared to 1. So you'll get R by Q omega and omega naught will go up. So we'll get R Q omega naught by Q into 1 by omega naught. So this is Z equal to 1 by omega naught. So the slope will be minus 20 dB per decade. Also, I want to point out, so here if you look at this a little more, this J omega by omega naught term corresponds to the inductor, and the minus J omega naught by omega term corresponds to the capacitor, right? That's kind of clear. So what this is telling us is that for omega much less than omega naught, the inductive impedance dominates over the capacitive impedance, and for omega much greater than omega naught, the capacitive impedance dominates. At omega equal to omega naught, the inductive and the capacitive impedances are equal in magnitude, opposite in sign, and therefore they become zero. Alright, let's do a frequency response of this Z, mod Z, or V with Is equal to 1. So here is a Bode magnitude plot, and I have put some values. Is is 1.1 nanohenry, 4 picofarads, and that gives us an F0 of 2.4 gigahertz, which incidentally is the frequency of all our Wi-Fi devices. And I've put R equal to 1 ohm, which incidentally is a very small resistance, right? Because this is a parallel RLC circuit. So usually the R will be large. But anyway, this is to start with. So what we see is that for low frequencies, the gain varies as plus 20 dB per decade, for high frequencies as minus 20 dB, and in between there is a flat region. And Q is 0.06 for this circuit, R square root C by L. Alright, now let us, so we discussed this already, at omega equal to omega naught, this becomes equal to R. Now the behavior of this function for frequencies close to omega naught as R becomes large, alright, is very peculiar, and it is very difficult to see just from this expression. So what we'll do is we just do a simulation. So here is what we'll do. So let me just simulate this circuit. Alright, so let us start with, so we say R equal to 1, and let's run this, and let's plot the voltage. So this is showing both phase and magnitude. We don't want to see the phase, so I'm removing the phase. So this is a plot which I already showed you. So this is for R equal to 1. Now what I want to do is watch this plot as we increase R. Alright, so if R is 1, this is the plot. Let us say R is 10. Alright, so what happens? Okay, so what has happened? The slope remains plus minus, but here instead of a flat, this has become a peak. Also, the peak magnitude has become about 20 dB or so. Earlier, what was it? It was 0 dB. Alright, so now it has become 20 dB when R is equal to 10. Alright, let's make it 100. See what happens. Wow, so now there is a very sharp peak in the Bode plot, and the peak gain has become 40 dB. Obviously, right, because this peak is in fact nothing but Vi times R, and I is 1. So I is 1 here, and R has become 100. 120 log 100 is 40 dB. So as R is increased, the peak magnitude of the RLC circuit increases. But not only that, you see this very sharp behavior here near omega naught. Alright, so omega naught is staying the same because it is 1 over square root of LC, and we are not changing L and C, we are changing only R. So okay, so this is 100, let's make it 1000. Let's see what that does. Alright, so very sharp peak, and this is where this circuit is so useful and widely used, because what we want, so this is incidentally, this is a band pass filter. Alright, it is a very narrow band band pass filter, because it is allowing only a very narrow band of frequencies to pass through, and any frequencies around here it is attenuating significantly. Also notice that the slope of this line very close to omega naught is much higher than plus 20 dB or minus 20 dB. So that is a property of the function of omega that this is. Alright, so let us just plot all these three. So for various values of, alright, so we get 4 plots on top of each other, R equal to 1 ohm, 10 ohm, 100 ohm, which you can hardly see, but it is here, and then 1000 ohms. Alright, so as R increases, one says that the Q, which is R square root C by L, the Q, the quality factor increases, and as Q increases, the Bode plot becomes much more and more narrow, making this a more and more narrow band pass filter. So in high frequency communication applications, where you want this filter to be extremely narrow band and pick up only signals just a few megahertz, around 2.4 gigahertz, these circuits are very widely used. Of course, they are used in combination with transistors, but that is a postgraduate level topic. But at the core of it is this parallel RLC, or more appropriately a parallel LC circuit, because R, as I said, is simply a kind of parasitic capacitance. A parasitic resistance. Alright, so these are simulations. So this is the same plot, just to conclude. And the Q varies from 0.06 to 60 as R varies from 1 to 1000 ohms. In real life circuits, Q is typically of the order of 10 or so. Getting greater than 10 is not that easy because of the non-idealities of the current source and the capacitor. Alright, that finishes this lecture.